Welcome, students. Today, we embark on a mind-bending journey into the fascinating realm of quantum physics. Quantum physics is a branch of physics that explores the behavior of matter and energy at extremely small scales, such as atoms and subatomic particles. It is a realm where classical physics falls short and the rules of the quantum world govern. Firstly, let's delve into quantum phenomena. Here we encounter some mind-boggling concepts, such as quantization and wave-particle duality. Quantization tells us that certain properties of particles, like energy and angular momentum, exist in discrete, quantized values. This means that these properties can only take on specific values, rather than any arbitrary value. Wave-particle duality, on the other hand, reveals that particles, such as electrons and photons, can behave as both particles and waves simultaneously. They exhibit characteristics of both, like having definite positions as particles, and displaying interference and diffraction patterns as waves. This duality challenges our classical intuition and requires us to embrace a more nuanced understanding of the nature of matter and energy. Next, let's explore quantum mechanics. Quantum mechanics provides us with a mathematical framework to describe and understand the behavior of quantum systems. It introduces us to concepts like superposition, where particles can exist in multiple states or positions simultaneously, and the uncertainty principle, which places a fundamental limit on how precisely we can simultaneously measure certain pairs of physical properties. Quantum mechanics also allows us to calculate the probabilities of various outcomes when measuring quantum systems. Instead of providing deterministic results like classical physics, quantum mechanics provides us with probabilities. This probabilistic nature reflects the inherent uncertainty and indeterminacy at the quantum level. Finally, the photoelectric effect refers to the emission of electrons from a material when it is exposed to light or electromagnetic radiation. This phenomenon challenged classical theories of light, which viewed light as a continuous wave. Instead, it paved the way for the development of quantum mechanics and our understanding of the particle-like nature of light. In the photoelectric effect, when light shines on a material, it interacts with the atoms or electrons within that material. The light is made up of tiny packets of energy called photons. Each photon carries a specific amount of energy, which depends on its frequency. The frequency of light refers to the number of complete oscillations or cycles it undergoes per second, and is measured in hertz, Gs. Now here's where things get interesting. For the photoelectric effect to occur, the light shining on the material must have a minimum frequency, called the threshold frequency. If the frequency of the light is below the threshold frequency, no electrons are emitted, regardless of the intensity or brightness of the light. However, once the light frequency exceeds the threshold frequency, electrons are ejected from the material. This phenomenon can be explained by the particle-like nature of light. Each photon transfers its energy to an individual electron within the material. If the energy of the photon is greater than or equal to the energy required to remove the electron from the material, called the work function, the electron can escape and be emitted as a photoelectron. It's important to note that the photoelectric effect happens instantaneously. As soon as the light reaches the material and its frequency exceeds the threshold frequency, electrons are immediately ejected. This immediate response was one of the puzzling aspects of the photoelectric effect that scientists had to grapple with. Furthermore, the intensity or brightness of the light does not determine the energy of the emitted electrons. Instead, it affects the number or rate of electrons emitted. Increasing the intensity of the light increases the number of photons, thus increasing the number of electrons ejected.